Alrighty, we started 1-2 with the knowledge that it was going to take a long time to cover everything that's in here because there are so many objectives. And what we're leading to is this process of when we graph, and somebody says analyze the graph. Analyze is a tricky word because it means everything that you could possibly know about this graph, tell us. And that's what we're going through, is all of the things that we could possibly tell somebody about a function and about a graph. So we've hit almost all of these. We're now down to the bottom of the pack. And today I'm going to talk a little bit more. In yesterday's notes, wasn't able to get through all of the symmetry problems. So we're going to talk about those that would involve radicals today, as far as even, odd, or neither. Now, like I mentioned to everybody that was here yesterday, we know that there are lots of other different types of symmetry. You studied those when you were in geometry. But at the pre-calc level, when we talk about functions, all we want to know is it even? So is it symmetric with the y-axis? Is it odd? Does it have rotational symmetry 180 degrees above the origin? Or is it not one of those? And that's the neither piece. And then we're going to determine if a function has any vertical or horizontal asymptotes. We're going to find that's a lot of review, but I'm going to add a little teeny piece of calculus in there today. And the calculus piece is something that will help you to understand why vertical asymptotes, horizontal asymptotes show up the way that they do. And it's the way you need to think as you move forward after pre-calculus. And then we're going to analyze the behavior of a function, which you also did in Algebra 2. So a lot of this is review, but kind of upping it a little bit, saying we got a little harder functions than we did in Algebra 2. So we are way back here somewhere. Yeah, down here. So what on earth page is that? This is page 26 in your note packet. So yesterday, we were cruising along with this in class, and we were just going to run out of time. So I said, let's hang on to the ones that are a little different, because they have the radicals going on for tomorrow, and talk about the even, odd, and neither with those. And G, I have absolute faith that everybody can do that one without a problem, because they kind of run the same way, Once you've done one, you have this feeling, oh yeah, when I raise it to an even power, it's going to be coming back positive. If I raise it to an odd power, it's going to come back negative. But then you get to this. And to check if it's even, odd, or neither, our job is to replace all the x's in the function with a negative x. And then simplify. Because we'll know if it's even if we can get right back to the original. It's odd if it's the exact opposite of what we started with. And then, if it's a mixture, well, then we have to put neither. So this is going to be -3 cubed roots of 8 times -x. So the first thing I'd do is say, well, that's silly. I'd write that as cubed root of -8x. But since this process is all about negatives, I start to think, could I simplify out that cubed root of a negative somehow? Sure I could, because this is really the cubed root of -1 times the cubed root of 8x. And I know the cubed root of -1. That's -1. So the -3 times -1 will make this 3 cubed roots of 8x. And then, scrolled up just a little too far, so let me scroll down. I take a peek at it. And I see I started with -3 cubed roots of 8x. And in this one, I've got my positive 3 piece down there. Unless I lost something. Let me take a quick look. I got a negative 1. Negative and a negative makes a positive. Okay? So, if it's the opposite of what we started with, then we want to call it odd. Did you guys watch yesterday's? So does it make sense with you that if it comes back exactly like how you started, it's even? I'm not seeing a lot of heads nodding here. Let's do this then. Let's back up a second. Even functions have symmetry over the y-axis. So here's what we're trying to show. Here's why it all comes together. I don't want you to just memorize it and, that's not how math is. Math is, let's think about what's going on. So if it is symmetric to the y-axis, it doesn't matter if I put an x in, bless you, or I put a negative x in. Notice that I get exactly the same y value. That's what we're checking for if we want to say that something is even. When I put x in, do I get exactly the same thing as when I put a negative x in there? But for odd, if I put x in, I get a positive y. And if I put negative x in, I get a negative y. So that's what we're watching for and trying to make this all come together. And these little boxes here are really important because algebraically, this says if we put a negative x in, we're going to get a positive back. That tells us this is even. And this one says if I put a negative x into this function, it's going to come back as the opposite of what it started with. And that's odd. And it's all because of the relationship between the y's. The y's are the same when it's even, and they're opposites when it's odd. So, we don't want to always have to graph these to tell if they're even or odd. We want to be able to do that algebraically. And that's what we were just doing here. Now we could confirm it by graphing it, and we would see that it has a 180-degree rotation about the origin, but that's as far as we want to go graphically. I mean, algebra is what we're trying to show here. So now, I wish I'd left myself a little more space for I, because when you look at I, of course you see there's a radical, but that's not really the radical that I'm interested in, because when I take a look down there, I see, well, that's a d squared. If I put a negative in there, that's going to become positive right away. It's that d to the 2/3 up there at the top that's interesting. So the first thing we'll want to do is make our d's negative, and then think about what happens when we have to raise a negative d to the 2/3 power. What happens when we have to take a negative d squared? And like I said, if you've done all the rest of these, you know this is just such a piece of cake. Negative d squared is, of course, positive d squared plus 4. But it's that numerator that's little, new, and different. And that's because it has a rational exponent. To understand this one, we have to do something that we don't do a whole lot, and that is to take a rational exponent and change it into a radical so that we can see what it is. And that's because typically if we work with radicals, it's easier to make them fraction exponents. But with this one, we'd have to remember since the 3 is on the bottom, it's the root. So it'll be the cubed root of negative d squared that represents that. So I think for a second, well, if I take the cubed root of negative d, that's going to be negative, but I'm going to end up squaring it in the end. So it'll be negative, but when I square it, it'll be positive again. So it is just d to the 2/3 over the square root of d squared plus 4. So we go through that process just to say, hey, is this going to come out positive or is this going to come out negative? I take a look at what I have. D to the 2/3 over the square root of d squared plus 4. Well, look at that. It's exactly the same as it was up here. So, t of negative d equals t of d. Whether or not we put a positive x in or a negative x in, we got the same y value, and that happens when you reflect over the y-axis. So that one's even. On that page, I think those were the two most challenging. Did you try any of the other ones on your own? Because like I said, we didn't get through them all in class yesterday. I think we did A, B, and C, and F, and then kind of ran out of time. Any of those other ones that you want to do together? You can look at them right now. So you're thinking you're good? Okay. Because that's one of the main objectives here was, can we tell? Even, odd, neither, algebraically, not necessarily graphing it. Graphing's a good check, but we want to algebraically. So if you did those notes and you started on the homework, you started to get a feel for, well, this is silly. If I raise stuff to an even power, it becomes positive. If I raise stuff to an odd power, it's going to be negative, and that's whenever we put the negative in there. So if none of the signs change, it's going to be even. And I think, well, that's going to come from anytime we raise it to an even power, it brings it back positive. If all of the signs change, then we're talking about odd, because it has to be the exact opposite of what we started with. Mixture. No, that's no good. Can't be a mixture. We have two types. Even, where it comes back exactly like it was. Odd, where it comes back exactly the opposite of what it was. If it's a mixture, then we put neither. Again, we're not going to talk about it's symmetric to the line x equals 2. We're not doing any of that. It's even, it's odd, or it's neither. So as you work through that page, or as you work through the homework, you notice, hey, if it's even on the top and even on the bottom, the whole thing came out even. So this was when we had our rational pieces, those that have the ratio of the fractions. And if it's even on the top but it's odd on the bottom, or odd on the top and even on the bottom, it came out odd. So we're talking about negative signs. If there's one negative, top or bottom, that's going to be negative. Now, if it's odd over odd, that's like a negative over a negative, which will make it even because it will be positive. And then, if we've got some mixture that gives us the neither on the top, and then it doesn't matter, is it odd, even on the other one, so it doesn't matter if we're talking numerator or denominator, that's going to mess it up and make it an even. So that gives us the ability to look at a fraction and say, all right, what's going on in the numerator, what's going on in the denominator, and tell whether or not we're going to be seeing an even or an odd function. So, next objective talked about the asymptotes. And the asymptotes are really important. You learned last year in Algebra 2 that that's something we have to find before we start. And we have to graph all of those before we grab the graphing calculator to figure out what it's going to look like. So it says, consider the graph of f of x equals 2x squared over 4 minus x squared. Well, first of all, I said this in yesterday's video too. Remember, the book is not putting arrows on there because they're just giving snapshots of like computer software or graphing calculator. We have to know, hey, this continues on forever. They did give us yesterday one of them where they had great big black dots to let us know, hey, this is stopping right here. So with this graph, I'm looking at the fact that I have a rational function, fraction. That's going to be hyperbolic. So I should have some branches here. And then I notice, oh, my denominator is factorable. That's a difference of 2 squares right there. And that's really important. Because as I start to analyze asymptotes and important features of this graph, one of the first things I know is you can't get a 0 in the denominator. That can't happen. And since neither one of these would cancel with anything in the numerator, they are my vertical asymptotes, my non-removable infinite discontinuities. So my vertical asymptotes would be at x equals 2 and x equals negative 2. And if I go over here, that actually would have been something we would put on here before we graphed it. But we'd like more information than that. We'd like to know, are there any horizontal asymptotes? How about x and y intercepts? What are some other important features of this graph? So, I'm looking at 2x squared over 4 minus x squared. And I'm saying to myself, I want to know what's going on as far as horizontal asymptotes. So as this graph goes to the left or the right forever, is it approaching a horizontal asymptote? So here's what I'm going to do first. I'm going to rewrite it in standard form. And then I'm going to take a look at it, and I'm going to think, okay, so if I go to the left or the right forever, what I'm really dealing with is infinity. So I'm going to substitute infinity in for x, like so. And now, we have to figure out what numbers would be important as we went further and further to the right forever. So to do that, I have to tell you a little story. It's a story that helps us figure out limits and how limits work. In Algebra 2, in the book, you always had this friend that made math mistakes. In just about every section, there was a part that said, your friend did the math problem like this. They made a mistake. Tell them what they did wrong. Well, you've got this friend, and this friend is talking to you about climate change, and you've gone on a vacation, and you took your friend with you. And you're at the Red Sea, and remember, your friend gets everything wrong. Your friend says, boy, look at how the water's going down here in this Red Sea. I don't know what we can do. I mean, climate change, bad stuff. I've got it! Every day while we're here, I'm going to come out and I'm going to spit in the ocean. If we do that enough, then the Red Sea will rise. That's what I'll do. I'll come out here. No, I'll spit in it. That'll make it higher. So, do you think if we all spit in the Red Sea every day that it would help the Red Sea to maintain its water level? This little 4, right here, is spitting in the ocean. If you're talking about infinity, imagine the size of some of those numbers as we go to the right forever as we're talking about infinity. This little 4, doing nothing. Infinity squared, and you're going to add a 4? You're kidding me. Hardly going to do anything. It's insignificant. And then I realized if I treat infinity like it were a variable, well, these two would cancel right out. And I'd be left with negative 2. That is my horizontal asymptote. The line y equals negative 2. So when we figure out horizontal asymptotes, we want to remember the size of infinity, the magnitude that the number infinity has. And that if we're just adding or subtracting a number, and sometimes even just multiplying by something, it's not having this great effect on the graph. So I could put this on. I'll use the same color I wrote it in up there. And then last year, you realized that sometimes your graphs do actually cross horizontal asymptotes. Now, that can happen in the middle of the graph. Here's why. What we just did up here was based on the fact that we were talking about going to infinity. Stuff way to the right on the number line, stuff way to the left on the number line. That doesn't guarantee it's going to work for the middle of the graph. So yes, sometimes our middle portion of our hyperbolas will actually cross our horizontal asymptotes, but not as we go to the right forever, then we go to the left forever. That will never happen if we have calculated those right. So like it says, can you identify the vertical or horizontal asymptotes from the graph? That's our job. You know, we want to be able to figure out beforehand the algebra that tells us where those are going to happen. We want to put those on our graph before we start. Notice they are dashed. They're either dashed or dotted, and that's because those are helper lines. To a mathematician, that says, this is not part of my final graph, but these things helped me when I went to do this graph. So, as we talk about horizontal asymptotes, I want you to remember your friend that doesn't get things right, and that they're going to try and spit in the ocean to make the Red Sea raise its water. Doesn't work that way. Now, can we or have we already figured out how to find vertical asymptotes? Absolutely. You know, you learned that in Algebra 2. That comes from those non-removable points of discontinuity. Basically, zeros of the denominator that won't cancel. That last year. And in Algebra 2, you learned, most of you anyway, you memorized what horizontal asymptotes do. That's what I'm trying to get away from by teaching you about those limits and spinning in the ocean so that we can say, hey, we have an understanding of why horizontal asymptotes show up the way they do. Because here's what you memorized last year. If the degree of the top is less than the degree of the bottom, then it's y equals 0. But you memorized it. And memorization is so bad because there's no understanding behind how things end up. So here's what we're saying. If we went through that whole process of the spitting in the ocean piece, and let's say we ended up with 1 over infinity, we have to start thinking, well, 1 over infinity, let's see. So we're talking about going from like 1/4 to 1/2 to 1/8, and you just keep going and you realize it's getting smaller and smaller and smaller. 1/32, 1/64, 1/128. This is getting closer and closer to 0 as a limit. And again, that's that little teeny calculus part that we're talking about. So if the degree of the top is less than the degree of the bottom, you end up with something with infinity in your denominator that tells you this fraction is going to get super duper small. When the degree of the top equals the degree of the bottom, y equals the leading coefficients. That's the one that I just did about, where our infinity squares canceled out, and +4 dropped out because it's spitting in the ocean, and we ended up with -2 over 1. And we use those leading coefficients as a fraction for y equals -2. Then, if the degree of the top is greater than the degree of the bottom, you don't get it. And that would be a situation that makes total sense because it would be something like infinity cubed over infinity. You do your canceling and you get infinity squared. That is never going to approach any certain number. It's going to continue getting bigger and bigger and bigger. We will never have a spot where we can say, hey, it's reaching here, because it will always get larger. So, I would love it if you think through this the calculus way. I also have the knowledge that some of you are just going to say, you know what, I remember that from last year, I memorized it, and that's just what I'm going to do with that. I'm fine with that too. But as you get closer and closer to calculus, you have to start thinking about this concept of limits. As we keep going further to the right and further to the left, what is happening? So that gives us another piece in our analysis of graphs. And like it says up here, horizontal and vertical asymptotes, the line y equals b, that's going to be our horizontal asymptote of the graph of the function. If f of x does approach a limit, as x approaches positive infinity or negative infinity, where is it reaching? So in limit notation, this is what we're saying. So like I said, teeny bit of calculus. The limit as x approaches negative infinity, so as you go to the left forever, your graph, f of x, will approach b. Closing in on that negative 2, getting closer and closer to negative 2. Or, this is coming from the left, this one's coming from the right. The limit as x approaches positive infinity for f of x equals b. So again, as we go to the right forever, what is it approaching? And the one I showed you, it was negative 2. Vertical asymptotes, the same thing is happening, but it's different because as they approach the asymptote, they're either going to go up forever or they're going to go down forever. So the line x equals a is a vertical asymptote of a graph of the function f of x. If f of x approaches the limit of positive infinity or negative infinity as x approaches a from either direction. So we will actually be talking about, in limit notation, what happens as you approach your asymptote a from the left. So as you come at it from the left side, what's your graph going to do? And I know you're writing, so I'm going to time to do that, but I want to go back to the picture and show you what they're talking about. So here's what we're saying. This is a vertical asymptote at x equals negative 2. As this graph gets closer and closer to that asymptote, does everybody see how it's going down? So it's going to negative infinity. Now, this one over here is approaching the asymptote from the right, but it's also going down. So that limit would also be negative infinity. So not only are we going to talk about those vertical asymptotes, we are going to say, this is what's happening as you approach it from the left. This is what's happening as you approach it from the right. That will be a part of our analysis. As your graph is coming into this vertical asymptote, what's it doing? Where is it going? Is it going up or is it going down? Positive infinity is up, negative infinity is down. All right. So this one has us going back to talking about our asymptotes, and we want to identify any horizontal or vertical asymptotes of this graph. And we can't help it. We tend to go right away to what we learned last year that we just had reviewed. And that's going to be, what are the zeros of that denominator? And so the hope is, hey, is x squared minus x minus 2, is that something that's factorable? Well, if we use x minus 2 and x plus 1, we've got it. Last times last will give us negative 2, inside times inside, negative 1. So that's going to give me vertical asymptotes, because they won't cancel, at x equals 2 and x equals negative 1. And we can see where that would fit with this graph. But now the part that we want to think about is the limits and horizontal asymptotes. So if I replace my x's with infinity, it would look like this. And I have to determine what up there in the red is spitting in the ocean. What's a pretty obvious spitting in the ocean up there right now? A number that's not going to make much difference to this one. Talk to me. What number up here isn't going to do anything as far as infinity is concerned? Yeah. Subtract 2 from infinity. Who cares? It's still a huge number. It's gone. Now this one takes a little bit more thinking. Think about when you square a number, about how much bigger it gets. Infinity squared. if we subtract infinity from infinity squared, we still have huge, enormous numbers. This, in this case, is also spitting in the ocean. Because just think about how the numbers grow when you square them. 2 squared, 4 squared. Just keep going with it. So now, I do my canceling. And I see that I'm going to have 1 over infinity. Okay, but as infinity gets bigger and bigger and bigger, this number gets smaller and smaller and smaller. So small that we won't be able to tell the difference from 0. Our eyes will not be able to see 1 over 128, 1 over 256. So this is my horizontal asymptote. And in this graph we see, oh yeah, look at the middle part, it crosses it. But the middle part is not what horizontal asymptotes are for. Horizontal asymptotes are for going to the right forever and going to the left forever. So our horizontal asymptote is doing exactly what it should do. Now the last piece has to do with end behavior, and that was our last objective. A horizontal asymptote gives one kind of end behavior for a function because it shows how the function behaves as it goes off in either one of the directions. So as it goes off towards either end of the x-axis. Not all graphs approach lines, but it is helpful to consider what does happen as you go further and further out there and out there, right and left forever. And like it says, they illustrate with a few examples here. So example 11 says, we're going to show you some graphs. We want you to use what you know from this entire section, actually, about functions and the math behind them to figure out which of these must match up with the others. So it says match the functions with the graphs in figure 1.35 by considering end behavior. All graphs are shown in the same viewing window. And I can't help it, the first thing I want to do is find the vertical asymptotes. So I'm looking at the denominator. And I'm thinking, well, that's not factorable. Oh, well, maybe I can find some zeros anyway. So I'll go ahead and subtract 1 from both sides. And then I'll take the square root. Uh-oh. The vertical asymptotes are imaginary. Well, that's not going to help me. I have some real stuff here. All right. Well, then maybe I better try the horizontal asymptotes. So I think about putting infinity in here. 3 infinity over infinity squared plus 1. Okay, well, plus 1 is spitting in the ocean. That's not going to do anything for me. I can go ahead and reduce, and this would be 3 over infinity. Well, as infinity gets bigger and bigger, that's going to get closer and closer to 0. So the horizontal asymptote for this one is 0. I go to the next one and I see, oh, all they did was, hey, they're adding 1x to the numerator every time here. So this one would be 3 infinity squared over infinity squared plus 1. Plus 1 is spitting in the ocean. The infinity squareds are going to cancel out. So this one would have y equals 3 as its horizontal asymptote. This one would have 3 infinity cubed over infinity squared plus 1. Get rid of the 1 because it's spitting in the ocean. But even if I cancel out the infinities, there's still going to be an infinity on top. So this one doesn't have a horizontal asymptote. And pretty obviously, since the last one increases that x by even 1 more, that one doesn't get 1 either. So that's helpful. That might help me figure out, which of these is which, but it takes 2 of them out of the picture, and you still have 2 of them to figure out. So here's what I want you to do. I want you to use the asymptotes along with the even versus odd behavior. And then I know you'll be able to figure out which ones are which. So in this one, we have an odd over an even. So this is going to have odd symmetry. This one has an even over an even. So that's going to be even symmetry, which again is over the y-axis. This one has third power over second power, so odd over even. That one will be odd. And the last one has fourth power over second power. That's going to be even. So you've got the little graphs down here. I can't leave them all up at the same time because they're too big. Graphs 1, 2, 3, and 4, and they're using little eyes there to stand for those. So see if you can match those up with the functions that we have up above. Just knowing horizontal asymptotes and whether or not it's even or not. See what you're doing. I also want to see what you're doing. You're backwards down there. And there's two ways to do it. I mean, they gave us the little, Roman numerals with the eyes there, so they're backwards. A is number 4, B is number 3, C is 2, and D is 1. So just knowing horizontal asymptotes and whether or not it's even or odd, that's enough for us to figure out this matching piece. And yeah, there's probably stuff like that in your homework. So we're using all these analysis pieces to say, here's what we know should happen. That way, if in the end we grab our graphing calculator to graph it, and it crosses something we know it's not supposed to cross, we know we punched something in wrong. And that's the most important part, is we're using that technology to help us, but we're going to know when we've done something wrong technology-wise. Well, that completed our gigantic list of objectives for section 1-2. So, like I said, tomorrow is basically a work day. The yellow worksheet, I think that went with 1-2 day 2. Yeah. So when you turn these in, when you submit them, don't forget to put in I think it was just one sheet, the yellow worksheet that went with 1-2 day 2. And then 1-2 day 5 is the thicker white packet of practice.